Assalamu alaikum. After HISPA, we have LTE, long-term evolution releases. So, so along with the work on release 8, the 3GPP was also working towards LTE. Uh, and release 8 that specifically include HISPA with MIMO and 64 QAM and dual carrier HISPA, and the specification of LTE, which is expected to substantially improve end user throughput, sector capacity, and reduce user plane latency, resulting in significantly improved user experience with full mobility. So this release 8 that was uh, published in 2008 include MIMO technology in it, 64 QAM capacity, dual carrier of HISPA. That was basically to pave the way for the LTE. The LTE was there to improve the end user data output, to increase the system capacity and reduce any delays that can be observed by the user when requesting for any services. So to that, there were some changes made in the LTE with respect to 3G. In 3G, we had WCDMA, whereas in 4G whereas in LTE we had OFDMA, that is orthogonal frequency deviant multiplexes, that is used as a transmission scheme in LTE. The new OFDMA based air interface is also referred to as the evolved UMTS terrestrial radio access. The UMTS terrestrial radio access are U-train that was with the 3G that uses WCDMA, whereas this EU-TRA uses OFDMA, that is orthogonal frequency deviant multiple access. And the evolution of system architecture powered by packet switched services optimization need new radio interface design, that is new opportunities. So in LTE we had only packet switching, uh, totally, uh, even the voice was also transmitted over the packets, that is voice over IP, no circuit switching was there. Flatter architecture, all radio functionality co-located in node B. So there is no RNC in there, or no BSCs like functionalities included in LTE. So all the functionalities are co-located in node B. The LTE overall network architecture, including evolved U-train and evolved core network, evolved packet core, previously known as system architecture evolution, is designed to be a flat and IP, all IP based. Flat means same, and IP means it's evolved in uh, access network as well as the core network. Whereas system architecture evolution started soon after radio interface development by release 8. So the main elements in the evolved packet core are the packet data network gateway PDN or PGW, and the serving gateway or the SDW, and the mobility management entity, that is MME. The packet gateway is the element which connects the user equipment to one or more external packet data networks, the operator network, internet etc. While SDSN, that is serving gateway, is the uh, which terminates the interface towards the EU train. The MME is a control node which processes the signaling between the user equipment and the EPC. The EPC includes the other elements such as the policy control and charging rules function, PCRF, and the home subscriber firmware. So PCRF similar to the IN that we had in GSM, and this HSS is similar to the HLR that we had in GSM, and is connected to the elements of other core networks, for example, SGRS and SGRS, that is serving GPRS support node. The LTE EU trend consists of a network of base stations known as evolved node base with no centralized controller. That is the meaning of flat architecture, as in we see in the previous architectures. We had in the BSS, we have BSC or RNC. So BSC or RNC basically was the centralized components or the controlling components all the base stations were controlled by the RNC and BAC. That was in the access network. And in the core network, MAC was there to control all the other devices. Even the BACs were controlled by the MAC. So that was kind of hierarchy architecture where base stations controlled by the BACs. BACs were controlled by the MACs, and MACs also connected to HLRs and other equipments, and MAC has the central control over there. But here we are saying it's a flat architecture. There is no centralized controller, and the base station are evolved to known as the evolved node base, E node base, and there is no RNC like component in the LTE architecture. Whereas its access network EU train is responsible for all radio related functions such as radio resource management, scheduling, header compression, security, connectivity to the EPC and others. Further details on EPC and e-train elements can be and functional can be found in this document, that is 3GPP-TS23.002. If you are interested, you can have a look at that document as well. So this is the flat architecture, flat LTE network architecture that you can see. It's a very different from the one that we have seen. If you compare it with the 2G architecture, with the 3G architecture, you will find very different from those architectures. See, user equipment is directly connected to E node B, and E node B is connected to serving gateway, and serving gateway is connected to PDN gateway. And whereas signaling is done through this MME, so this E node B is also connected to MME. MME is connected to SGSN, that is the serving GPRS support node, and HSS home subscriber station, and is also connected to the serving gateway. So these all are the signaling links with the ACE, so that is used for the signaling, and serving gateway and PDN gateway also share a signaling link. PCRF, that is for the charging purposes. EPDG, trusted non-3GPP IP access, and this is trusted non-3GPP IP, trusted or non-3GPP IP access. So the architecture become very simple. And there's, you can see there is no, you cannot differentiate this one. This is EU train, or this one the core network. So core network and access network are kind of working together. You cannot really differentiate which part you can say it's access network and which part is the core network, because it's a flat architecture. So many of the targets implied that a flat architecture would need to be developed. Flat architecture with less involved nodes reduces latency and improves performance. So the development toward this direction has already started in release 7. So this is how your different nodes has been removed from the LT architecture released in 2008, from 2006 to 2008. So these were the developments you can see. First, we had the node B connected to RNC, to SDSN, GGSN. Then in release 7, we tunnel the direct connection between RNC and GGSN rather than via SDSN. Then we remove this RNC in release 7, and then we have direct tunnel with RNC and node B to SDSN and GGSN. And then we have E node B, that is a combination of all the functionalities of RNC including node B, and we call that E node B, and that is directly connected to SAE gateway. And in between for signaling, we have MME. So this is another interface, that is new interface introduced in U-Train, that is X2 interface that connect one E node B with another E node B. Previously, the base stations, not all base stations were connected with each other, but here it is necessary that each interface, each E node B should be connected with another E node B. So that is There is something very different in the LT architecture with respect to the previous generations architectures. So EU train, which contains a new network element, the E node B that provides the EU user plane and control plane protocol, terminates the user equipment. A new interface called X2 that connects the E node Bs as a mesh network, enabling direct communication between the elements and eliminating the need to funnel data back and forth through the RNC. So EU train is connected to the EPC via the S1 interface, which connects the E node base to the mobility management entity and serving gateway elements through a many-to-many relationship. Functions of E node B, basically these functions are the combination of functions performed by base station, a simple base station, and RNC. All those functions are included in node B, and we call that new the evolved node B that has the functionalities of radio resource management. Because there is no RNC, then this radio resource management is now the function of node B. IP header compression and encryption as all IP networks, so IP will be there. So layer 3 header compression and encryption is the job of now node B. Selection of MME and user equipment attachment. That is the signaling element will be selected. Routing of user plane data toward HGW, scheduling and transmission of paging messages and broadcast information, Mailman and Mailman reporting configuration for mobility and scheduling and transmission of ETWS messages. Non-access start and signaling and signaling security, access start and security control, idle state mobility handling, and ETS barrier control. Mobility anchor point for inter-node handovers, termination of user plane packets for paging reasons, switching of user plane for user equipment mobility. These are the functions of the serving gateway. This is the LTE protocol stack that you can see from user equipment to E node B on physical layer. We have physical layer, MAC layer, RLC, and PTCP. These are the protocols that use on the layer 2, whereas from user equipment E node B and to MME, we have different set of protocols. So these are your access startup protocols and these are your non-access startup protocols. So the protocols running between user equipment and the E node B are known as the access startup. So these are your access startup protocols. And the protocols between user equipment and MME are referred to as the non-access startup protocols. Latest release of the LTE is in 2009, that is release 9. As LTE standardization reached a mature state where changes in the specification are limited to corrections and bug fixes. Release 9 introduces enhancement to both HISPA and LTE, such as support for home node B and E node B, that is femtosys, the evolution of the IMS architecture, ETC. Throughout 2009, the 3GPP worked on a study which identifies a number of LTE improvements in order to meet IMT advanced requirements. In September 2009, the 3GPP partners made a formal submission to the ITU proposing that release 10 and beyond LTE Advanced should be evaluated as a candidate for IMT Advanced. So some of the new technology components of the LTE Advanced are that is carrier aggregation, where multiple component carriers are aggregated to conform bandwidths of up to 100 megahertz and therefore achieve higher data rates than in LTE NAS uplink and downlink transmissions. So it's in carrier aggregation. Normally we had like a chunk of frequencies. That chunk may be of 5 megahertz, maybe 10 megahertz. But with carrier aggregation, you can have different chunks of bandwidths in different frequencies. Still, you can combine them and you can count that as an aggregate bandwidth. So that is the advantage of having the carrier aggregation, and that is allowed or the acceptable in the LTE Advanced release, release 10 and beyond. Then the coordinated multi-point transmission and reception to improve performance at the cell edge and relays to improve coverage and reduce deployment cost. So this will also encourage and also discourage the installment of new base stations if there is some uh, power issues with the same edge users. We can have the coordinated multiple point transmission. That means a relay basically that will improve the coverage and reduce the deployment cost. Release 10 also include quad carrier operation for HISPA plus, that means four carrier operation for HISPA plus, and is currently defining the scope and timelines of for the release 11, which will provide further announcement in ports LT and LT advanced. Then we have LTE OFDM and SCFDMA. Information is modulated only to one carrier, adjusting the phase or amplitude of the carrier or both. So transmission bandwidth, that is center frequency. So the difference between OFDMA and single carrier FDMA, that one is multi-carrier access scheme and one is single carrier frequency driven multiplex access scheme. Multi-carrier means we transmit our data or modulate our data over to multiple or the sub-carriers rather than transmitting it over the single carrier. The advantage with OFDM is that if any one of those sub-carriers uh, get serious fading, then that only that information will be lost. Other information will remain intact and can be received correctly. And when in 1,000 bits, only 2 bits are like in error or few bits are in error, you still have the room to fill the gap that of those 2 bits by improvising information, and no need to retransmit that information. So that is the advantage of OFDM, where we have the selective fading particularly. In case of selective fading, OFDMA is very much popular access scheme to be used. Whereas in single carrier, we have only one carrier is used for the transmission of data, and if flat fading occurs, sorry, if frequency selective fading occurs, then you need to retransmit your data because your transmission has been faded and that cannot be received properly as a receiver. So that is the comparison between single carrier versus OFDM. This is single carrier transmission using WCDMA. You can see 5 megahertz. Here we have typically several hundreds of carriers with a spacing of X kilohertz. And within the 5 megahertz, you have carriers. They are orthogonal to each other and they carry few bits of information. And large, this 5 megahertz is divided into many subcarriers. Maybe we divide 5 megahertz by like 10 kilohertz or maybe 50 kilohertz. Each carrier will have of that size and then will be carried out. So another figure is here that shows you the difference between the two single carrier and OFDM. So here we have 15 kilohertz of subcarriers and this is one OFDM symbol. In between, we have cyclic prefix, and then we have another OFDM symbol. And if you say different colors shows you the different data of different users or the different modulating symbols. Then there are four symbols being transmitted. So one symbol is that is of one is being transmitted on one carrier, another on one. So these are divided in frequency and separated in cyclic prefix, that is in time, and they are transmitted. So this information, like few bits are transmitted here, few bits are transmitted here. So if any fade occurred here, let's suppose यहाँ पे कोई fade आता है, frequency selective fade. So one of these frequencies will be affected. Means the information of a particular user will be affected, but others can be transmitted. But here we can see the 60 kilohertz. So this 60 kilohertz information here against 15 kilohertz. So this will be of much information. Means we combine 15 kilohertz for information. The चार information transmit combine करेंगे, then we will have this one. So if any fade occur here in 60 kilohertz, all this 60 kilohertz bandwidth will be wasted. But here, if any fade occur, we will be wasting only 15 kilohertz. But here, the waste will be 60 kilohertz. Means you have to retransmit this again. So that is kind of advantage of having OFDMA. So data symbols occupy 15 kilohertz for one OFDMA symbol period, whereas data symbols occupy m into 15 kilohertz for 1 over m SCFDMA symbol periods. These are block diagrams, they are self-explanatory, just go through them. So there is another difference between OFDM and OFDMA. Only one user can transmit during an OFDM symbol. Subchannelization enables several users to transmit at the same time. So OFDMA, for OFDMA, it is very necessary that your source data source bit should be converted from serial to parallel. Then we have the modulation of these parallel bits, and then we have the IFFT, and then we will modulate them to the RF frequency. So it's also used in digital video technologies and wireless local area network. Reason for adoption of OFDM in LTE that it has good performance in frequency selective fading channels, low complexity of baseband receiver, good spectral properties and handling of multiple bandwidths, link adaptation and frequency domain scheduling, and compatibility with advanced receiver and antenna technologies. So these are some of the advantages and challenges of OFDMA. The advantages of OFDMA only became significant and possible due to recent developments where system bandwidths getting larger than 5 megahertz, causing receiver complexity and important issue and the radio access network architecture with radio related control being set up at the base station. Challenges of OFDMA include tolerance to frequency offset and high PAPR. High PAPR is that we already learned in the lab. That is the problem with the multi-carrier communication systems. That when we add the subcarriers, when they add in addition, when in phase, their maximum amplitude go beyond the saturation level of high power amplifier. That will force the HPA to go into the saturation range, saturation operation, where it will be clipping the excessive voltage that is not in the operative range of this high power amplifier. So that will be loss of information if we have this PAPR occurrence. This is the comparison between OFDMA and CDMA transmission bandwidth. Attributed transmission bandwidth, CDMA full system bandwidth, variable up to full system bandwidth, frequency selective scheduling not possible in CDMA. A key advantage of OFDM, although it requires accurate real-time feedback of channel conditions from receiver to transmitter. Symbol period very short, inverse of the system bandwidth very long, defined by subcarrier spacing and independent of system bandwidth. Equalization difficult above 5 MHz, easy for any bandwidth due to signal representation in the frequency domain. So LT transmitter and receiver, you can see modulation, translate serial to parallel IFT and cyclic extension. Receiver, remove the cyclic extension, serial to parallel conversion, FFT, and then we have equalizer and demodulation. So during transmission, we have IFFT, and during reception, we have FFT. Then we have LT MIMO, that is multiple antenna at input and multiple antenna at output can be used. It has advantages. It provides you spatial multiplexing, pre-coding, and transmit diversity. It has type CISO, MISO, SIMO, and MIMO, single input, single output, multiple input, single output, single input, multiple output, and multiple input and multiple output. So that concludes this lecture. If you have any question, you can ask from this lecture. Uh, Today we had only one class, that is from 2. So I just take that class in advance at this time because I am available at this time. At 2 o'clock, I am not available. So if you have any questions from this lecture, you can ask. No. So thank you for this lecture, for your time. I'll see you in next lecture. Inshallah, Allah Hafiz.